SwayamPrabha. Digital India. Educated India.
So, yesterday's questions I have written there. I think what does a chemical engineer do, and below that we have written research, and research we have discussed, and next one was process development. I think I better write for continuity sake. Research, process development, process design, and evaluation. Then we have plant design, I think I have written plant design, operation, construction and operation. The operation, then product supervision, plant technical service, product sales. Okay. So, these are the things we have been discussing. I think quickly I have to go through, and research we have told three types. This is basic research, exploratory research. I think you have to remember these words. I think you have to make a note of that. And third one is process research. In process research, what do we do? In exploratory research, we will try to find out which catalyst is better and all that. In basic research, how the catalyst is working, how the molecules are moving, where they are getting adsorbed, why should they get adsorbed there only, why can't they go somewhere else. All that basic questions are answered in the basic research. And exploratory research, particularly in industry, when you do not have much time, you try even ammonia, 20,000 catalysts it seems they have tried. I will send you one beautiful, you have to collect IDs of all the, you are doing that, So, I will send you some information. I got one paper today, I think the title also is which saved the world or something. So, it is about ammonia process, where there was a chemist who has patiently tried 20,000 catalysts of different combinations. So, finally, they could come up with this iron with some mixed metals. Otherwise, originally it is osmium and something else, where Haber actually did it, but that is not practical. So, that is why Haber also got Nobel Prize for what he did. He proved that it is possible to produce at large quantities, and the other person Bosch, Carl Bosch, he also got Nobel Prize, and how much work he has done in beautifully written in that paper. I will show it to you, that you will be proud to be chemical engineers if you read that. How many things one has to do, even this, all these things I have written there, you can be lifelong a research chemical engineer. Okay, that is your profession. So, this is what chemical engineers do, means you are not going to do all these things. If you are doing all these things, you cannot do anything, okay, because I think you are not expert in anything. So, that is why you can choose that if you are interested in research, if your brain is very sharp, and if you want to put your brain always under very sharp conditions, then this is the best one, because always it thinks that something new, something new, something new, right. And then this process development. Process development, I told you, once you have the process design on a very small scale, maybe 1 kg in the laboratory, and then you can try that various equipment also will be there under process design. But whereas in exploratory design, exploratory research, you are only concentrating on the one aspect, catalyst alone. So, like that, for example, it is not catalyst, in some other process, maybe how the bubbles are moving in a bubble column reactor. Okay. So, all your research is only on the bubbles. What kind of bubbles you have? How do you want to? Normally we would like to, all of us enjoy very spherical bubbles, but unfortunately if you look at the aquarium, all of them are not spherical bubbles. Some will be like this, hat shaped, some will be slugs if the diameter is very small, okay. Some will be very beautiful spherical bubbles. So, I mean all chemical engineers should fall in love with only spherical bubbles. Why? Easy for what? So that
easy for measurement and
easy for measurement. If you are able to measure the diameter, then you can find out what is the surface area, and we know that in all these processes surface area is very important, because all these whenever you have heterogeneous system, it is the interfacial area or surface area which is more important. So that is why spherical bubbles are very easy to, but unfortunately life is not that easy. So that is why you have to live with slug shaped bubbles and also hat shaped bubbles and some spherical bubbles, and also not only that, some large bubbles, some small bubbles, all combinations. That is why we say bubble size distribution, and lifelong you can work only on these bubbles. Drops, okay. Particles are not that difficult, and you will never get a spherical particle, and always in the class we would draw only spherical particles and then write what is entering, what is leaving through this particle and all that, but you will never get a very beautiful spherical particles except when you are playing this marbles. Those particles are beautiful particles. No chemical industry can produce that kind of particles per catalyst, okay. That is why most of the time they go for the cylindrical particles, easy to produce, right. So that is why in this process design, process research, when we are talking about small scale, getting as much information as possible, starting from heat exchangers if there are, and small condensers if you want to have distillation and condensation. So all kinds of things you will have. Then come to this level, process development. In process development you focus on pilot plants. Why should we do that? I told you already that because I do not know whether straight away from process research to industrial scale, when I go, I am not confident whether things will work or not, right. Most of the time it will not work, right. The reason is all the chemical engineering processes are all means, I mean most of them are only heterogeneous systems. In heterogeneous systems, either you have bubbles, drops or particles. In fact, if you understand bubbles, drops and particles, you understand whole chemical engineering, right. In any system you see, you will have either bubbles or particles or drops, and all of them behave differently. The way bubble behaves when it is moving is slightly different than the way drop moves, and when compared to these two with the particles behave in a different way. So that is why that behavior is very important inside the reactor, how they are moving, right. So that is why you have to get that pilot plant level. You should have studied already in your process design course. I think you should have some process design course, right, where process design and economics or process equipment design is different, where you calculate the total time required for the complete money recovery once you design the plant and then try to operate. Process plant design and process economics, So I think you should have different universities have with the different names. So in all that also, always we talk about pilot plant. Pilot plants are very costly. If you are able to really predict, or nowadays with the computers, if you are able to simulate the entire pilot plant and able to see that what are the problems you may face at a pilot plant scale, that is why CFD will help you, okay. So with the latest softwares you can do that also, to avoid the actual construction of a pilot plant and collecting data. Instead of that, if you are able to create the entire pilot plant on computer and then try to simulate. Simulation means trying various parameters and then every time recording what is happening at the end of the simulation, because your target is to produce maximum amount of material with minimum amount of cost. That is what is the whole chemical engineering process, right. So that is why this pilot plant scale we cannot avoid, we have to go through that. Unless you, I think every one of you, that is what I told some of you would have told that chemical engineering is already saturated. It is not saturated. only his brain is saturated, he is not able to see the problems. So, if you make your brain sharp, you can always try to find out some improvement. In fact, in our department now recently the trend changed the last 5-6 years, but always what we have been doing in our department for the last 30-40 years is that how to improve the performance of a equipment. It may be a heat exchanger, it may be a distillation column, it may be a reactor, okay? And in reactors, how many kinds of reactors you can see? Basically we can divide them only into 3 parts, okay? I mean ideal reactors. But if you look at the reactors, you have fluidized beds, you have packed beds, we have moving beds, and we have bubble columns, right? And we have again liquid reactor, what is that, mixer settlers. Mixer settlers also are reactors, okay? And you have rotary kilns, right? But rotary kiln also can be imagined in the one of these perfect ideal reactors, okay? But all these reactors are there. That is why lifelong people will work only on the improvement of rotary kiln. It is not that easy, that very slowly, sluggishly move, very slowly. The speed is only 5 rpm or less than 5 rpm. You cannot put 100 rpm, okay? That is only for fans and all that, right? But you cannot. So, the moment you put 100 rpm, that won't act as a reactor, okay? And lifelong people can work only on that, or only on fluidized bed, or only on packed bed, or only on slurry reactor. A slurry reactor has 3 phases: gas, liquid and solid, like your production of hydrogen, hydrogenation of vegetable oils, dalda and all that. So, you have catalyst as Raney nickel catalyst, and liquid as oil, unsaturated oil, and hydrogen as the gas. You have 3 phases. So, lifelong people will work only there, okay? So, that is why you have to choose one of these steps and then try to find out where your interest is. That is why what does a chemical engineer do means, it is not that he is doing all this. You have to choose either that or this or this, or at the last. I think this is the easiest one, okay? Because this is what they do in MBA management, okay? Product sales, okay? You can go and talk to them happily in English, but you should have good English, okay, to convince them. Even I think you can say right wrong as right. So, by convincing them, then they will buy something. That is what people come and then sell soaps and powders and all that. I pity them most of the time. When they come, immediately you will say go away. I think it's in the houses when they come Saturday, Sundays. It is very unfortunate, but still we do that. It is very bad. So, this is what is the easiest one. Without brain you can do this, but only with mouth talking. All other things definitely they need lot of thinking and lot of knowledge from chemical engineering. And okay, so then process development is pilot plant scale, that you can remember that process development means pilot plant scale. And at the end of that, what you normally have is that lots of data on whatever doubts you have. For example, fluidized beds are terrible reactors. Even now we do not have good procedures to design a fluidized bed reactor. What is the problem? You have the solid particles, gas will go, and the particles will behave in a different way. Gas also behaves in a different way, and the gas creates large bubbles inside the solids, and the diameter can be 3 meter, 4 meter, like a big well. 3 meter, 4 meter diameter, it is not small, okay? So, under those conditions you have tons and tons of solids there, and you have to send gas to fluidize. I hope all of you know what is fluidization, right? All of you have studied this in fluid mechanics. I am sorry for chemistry people, but I think chemistry people have to slightly work more, that is catalyst. Particularly I think in catalyst, how many people are there chemistry background, how many people are chemical engineering background? 4 are there, right? Chaya, you are Chaya, right? You are chemistry, yeah, chemistry, chemical engineering. One more? Oh, two. Okay. I think 2 of you should teach them after the class is over what I have talked. So, that way you remember, as well as they will be also comfortable. Please help them, okay? I think because they may not understand what is fluidized bed, and of course, only 2 people will be out of class, even though physically they are present here. So, that is why I do not know how to take the simple examples. I think they may not know the simple reactors also, but slowly we make them understand, but I think you can help them, right. Yeah, it is very difficult to have direct scale up for the fluid agent beds. So, that is the reason why you have various scales of fluid agent beds finally to design the final one, large scale one. Okay. So, that is why you have lots of data how the bubbles are moving if it is fluid agent bed. Even bubble columns are that is not easy, because when you take a small nice this size reactor and then bubble, you will get very nice bubbles. Now, in the industry this kind of size reactors no one will use. Okay, there will be again 2 meters 3 meters diameters bubble columns and height may be again 4-5 meters, right. So, you do not even know that how much gas you have to push through to keep that the bubbles move. That is why pressure drop and all that we calculate, compressors and all that we use, right. Even blowers will not be sufficient, only compressors will be sufficient, will be required. So, then the bubbles will move, will be moving, but here maximum size it can go maybe let us say 5 mm or 6 mm or 10 mm bubbles, but there this to start with itself you may have 1 feet diameter bubbles, 1 foot diameter bubbles. So, then how do you tackle them? That is why the scale up problems come in chemical engineering, and in other engineering it is not there. For example, in cars, automobile design of mechanical engineers. So, whatever car size outside, body and back side, dicky, front side, engine, all those things only will change, but the engine size will not change much. Depending on the capacity, they may have slight variation. So, that is why they have control over combustion there, right. That droplets combustion, when they spray and a spark plug will start and then it will burn and that volume increases, so it moves the pistons, all that. So, that is very easy to imagine, and there is nothing more to that except what kind of fuel you use. If you change the fuel, what will happen? Nowadays we want to use alcohol as fuel or oils, some oils as fuel, all that. That is what is the research what they do, but the basic shape of the engine is not changing. But in chemical engineering every equipment changes, every equipment in that flow chart. So, that is why in the process research here you will have approximate idea of what are the equipment that are coming there. Okay. In the process research, that means very small scale. Then you go to this scale and then you just a little bit magnify all those equipment, then you have to collect the data how the bubbles are moving if it is bubble column, or even heat exchangers. In large scale diameter generally heat exchangers behave properly, right. But in spite of that, how do you distribute uniformly through the tube side and also what that shell side, all that information you have to collect. And if it is reactor, you have to collect lots of information temperature wise and also the kinetics, all that you have to see that what you get in the laboratory also happening in the pilot plant scale. So, that means you have lots of data there, and with that data go to process design and evaluation. What you do there is everything on the paper you should now draw the flow chart in the process design and development. Process design is different and equipment design is different. In equipment design actually you produce the equipment size, right, volume, and whereas in process design you cannot say that the volume of process is so much, but there what you have to do in process design is the steps like flow chart is exactly like flow chart development. The real flow chart, the final flow chart which you see in Shreve and Dryden, most of you have used that, those flow charts are developed here. Probably you may be thinking that why the hell I have joined chemical engineering. Okay, I think it is so much difficult, it is not that easy job, that is why we must be proud of that. How much information is required for one process to develop. That is why if after collecting all your email IDs, I will send you that paper. It is only 2 pages, but how beautifully it is explained and how much work is involved in that, right. And Carl Bosch, how much work, I think he is a chemical engineer, but I thought he was a mechanical engineer converted, but they straight away said he is a chemical engineer. But because I said that because at that time there was no chemical engineering in Germany, okay. As far as I remember, maybe technical chemist or something may be there, but I think how much work he has done and his team, how many things, I think for everything is a big problem for him, okay. That is at pilot plant scale, because the pressure is around 300 atmospheres and the temperature is around 500 to 550 centigrade. Temperature is okay to maintain, but the pressure to go to that level is not possible. That is why that is the simplest reactor what they have, and I think this is the reactor, and all other things are to pressurize the system, that is in the laboratory what they have used, and that one must be the compressor where it keeps the pressure high, and with that too the next one to this level he has gone. That is the reactor. Dimensions are not given, but I think I will show you next one. This is what I told you I have seen in the University of Karlsruhe, right. There is a guy also standing here, that is me. Okay. Yeah, you can now imagine my height is only 5.5. Now you can measure how many 5.5s. Okay, how many? 6? Yeah. So maybe 30-40 feet, right, at that time, and they have produced this. That is what is the information that was there. I think this is in 1913, and 1908. What is the first one? Okay, 1908. Yeah, 1908. He just proved the concept that it can be done, and then they handed over to Karl Brosch in that BASF company. From then onwards, day and night they worked. In 1913, they have designed the whole thing, and then finally they have produced, I think, 7,200 tons per metric tons, I think must be per annum. Then afterwards also I had some other information. I think by 1921 it has gone to 72,000, I think, and then afterwards it went to 450,000. That is almost 500,000 tons. That is in 1991. Okay, using the same technology. Even now people use only iron catalyst, right. Okay, so that is what, and this is what, yeah, and this one, that is in German language. This is Hochdruck means, I mean, I know a little, high pressure reactor for ammonia synthesis. Nach means after Haber and Bosch. Haber is the scientist and Bosch is the chemical engineer. Then this is entwickelt means developed, developed at the university. Technician Hochschule Karlsruhe. Karlsruhe, they call Hochschule means high school, technical high school Karlsruhe, that is what, that is developed there, and this is from 1923 to 1982. This reactor at 500 degrees Celsius and 300 bar produced 1 million tons of ammonia. How many years there? From 1923 to 1982. Right. After that they have removed that reactor and then again put another reactor. Everything was a problem for him, because the hydrogen being the lightest molecule, then it used to diffuse through the reactor. That means through the interstices of the metal parts in the wall. So it used to come and it used to diffuse and come out. So what happens, it seems after some time the strength of the wall will go, it will burst. Okay. So many problems, all these problems beautifully he has solved, and that is what is happening in each and every process. I tell you, in each and every chemical, if you take, we are talking about ammonia, you take sulfuric acid, you have the same stories. Okay. You take for example sodium chloride. Sodium chloride is salt from sea, we can easily get. No, not sodium, sodium bicarbonate. What is washing soda? Oh, yeah, production of that. And chloroalkalis, many compounds. All this, everything will have a story. How to produce benzene, you will have a story. How to produce toluene, you will have a story, right. So if you take chemical technologies, everything is stories only, because we don't tell the stories there, but we just give you only the final flow chart with all the conditions and all that. So for every condition to be fixed either in distillation column or in heat exchanger or in reactor, people would have struggled there. So much sweat and flesh has gone to produce each and every process. That is why I am proud of chemical engineering. I really enjoy. I think whenever someone talks about chemical engineering, my volume will become double mentally. So because I think so happy. So because I think we are the people who are dealing with very complicated processes, and we don't have a one rule, for example, like that one rule in the sense, okay, we have now developed a process for sulfuric acid. Can I use the same process, same information for producing nitric acid? This is also acid, that is also acid. No, you cannot. That is the problem. Not only that, in organic synthesis only one molecule will change, in that ring, benzene ring for example, only one molecule will change. So, one molecule changed, okay, it is almost like benzene only. So, let me do the same process here, means you cannot do that. Totally you have to think differently, kinetics will change and your temperatures will change, pressures will change in the reactor, everything will change, and everything starts with reaction, everything starts with reaction. So, that is why I think really start loving chemical engineering and then try to learn at least now more interesting subjects, and every subject is interesting in chemical engineering, including chemical technology is very interesting. If the normally we do not know how to teach, so that is why you are getting bored. But if the way Russians have developed, I think the Russians chemical engineering, chemical technology books, I do not know whether you have seen or not, you would have not born I think at that time. So, there was one publication called Mir publication, MIR, Mir publication. There was a lot of translations from Russian to English, but there every process they start with reaction, thermodynamics and other steps, and everything together one by one they do that. Tried that I think in some of the flow charts, but Shriv and all that directly statistics they give, then process they give, and process also so much details you get fed up, because we are only reading that as only for our examination, but industry people love that. Why? Because in industry every step is important, every information given there is important. For if they open the Shriv book, I hope I am talking only English, no? Shriv, okay, Shriv book, yeah. So, Shriv book has also a lot of information for industries, right. So, that is why I think every process has this kind of problems which have come through all these steps. The step 1, step 2, this is pilot plant level, step 3 is the actual flow chart development level, and economics also will come after drawing the flow chart. Now, calculate in each step what is the cost, what should be the even sizing of the reactors, everything you have done there in the flow chart, all the information is there. That means just before constructing house they will have the blueprint, right, for plan and all that, everything is there with you for the process, right. So, at that point of time what is the size of the reactor, how much material is used for the reactor, what is the material cost, and what will be the temperature, if 200 degrees centigrade how much energy has to put, energy cost, everything you have to calculate and then evaluate whether the process is economically viable or not. That is what is process design and evaluation. And unfortunately, it is not economically viable. What do? Start again from here, again exploratory research or basic research or process research, and then onwards again pilot plant, all that. So, that is why even though you are doing that, it is not guaranteed that you will be successful every time. That only gives us kick, If you are not successful, again with more vigor you have to come and try to solve the problem, not run away or not take bottles. Okay? No use of taking bottles. I think you are not deceiving anyone, you are only deceiving yourself, because whenever we are depressed we go for bottles. Okay? And these bottles also I will tell you later what kind of process is that. It is a horrible process. Yeah, I mean if you know the actual process you do not even drink that. Okay, anyway, so process design and evaluation. Okay, we know that only microorganism is doing, I think it is different. Okay. Yeah, process design and evaluation, that is the one. Then we have the plant design. Once it is economically viable, then go to plant design. So, give maybe here mechanical engineers are more, they can help us, right, construction wise. So, we know very clearly that this is what you have to fabricate, this is the size of the reactor, that is the diameter, that is the height, this is the thickness of the wall you should have, okay, and then nuts and bolts, everything, that part. I think some of you who worked in industry, you should have known all this. There are now companies specializing only in this step, right. Once you know this step, process design, on the paper you have all the information, what is step 1, step 2, step 3, what are the equipment, all that. Then afterwards they will convert everything into plant design, where they will go and then nut and bolt they start constructing. After construction, and they have to operate, that is what is that first time you call Commissioning, and also the first time what we call is
Erection EPC company.
erection and
Procurement.
online,
Procurement.
sorry,
Pre-commissioning.
not pre-commissioning,
Procurement.
startup. Yeah, no, startup. Actual starting up is really problems in chemical industry, right? Because that is the first time you are starting the entire process. So that means it starts with reactants, and then the reactants have to flow from, they have to get heated up and then go to the reactor and then react, come to next one, and then if it is a distillation process what you are using the separation, then you will have, it has to go to distillation column and all that. Because first time you do not know where it is blocked, or it may be blocking somewhere, and you do not know whether you have opened or closed, even though you have taken sufficient care. So that is why people are really worried at the time of this startup. Okay. So that is what it operation. Then once of course smoothly everything happening, then we have the product supervision. This is what I think most of us prefer to be as chemical engineers, because here the work is not that much except just looking at the reactor whether there is something going on, suddenly something may go wrong. And in this, at this level you should be more, you should have very good personal relationship with the workers, with the operators. Otherwise I am an engineer, you are an operator, you do means he will say go to hell or go to the reactor, go inside the reactor. Okay. So that is what they may tell. That is why that human relations also are very, very important in chemical engineering, because after all these steps are over, next is only human relations, and then the next one is plant technical service. So that means this man will be operating and then looking at the reactor or heat exchanger or distillation column. If there is suddenly something wrong, then he will call you, I have a problem, come here. He won't solve. Okay. He is only problem recorder. Problem solvers are here, plant technical service, or steam is not coming at the required pressure, or water is not flowing, or the reactants are not flowing at the required pressure. That means they cannot enter the reactor. So all that problems will be solved by this technical service. Then without any problems, if you are able to produce, then the product comes, and that the product, how beautifully you can pack, all that imagination. I think there is also here also there is of course sales people, I am not talking, but other than that, how do you pack these products? Nowadays I think most of the products we are alarmed with the packing, inside there may not be anything, but still I think you see the packing and then take it. Okay, including I think chocolate, what a kind of beautiful paper they make, it is a waste, because they simply throw it out and we eat. Correct, no? I think what do you do with that paper? You don't do anything with that paper. So beautiful paper, very costly. That also we have to be proud that we are only producing that paper. Very nice paper. It can be paper sometimes, it can be plastic sometimes. And what kind of packing is coming nowadays? Tremendous amount of varieties of packing, right? So all that. So this is what is the one the answer for overall all the answers for the second step. What is the second question? What is the second question? What does a chemical engineer do? Okay. Please remember these things at least. That is why I tell you now when you go to your room, catch one computer science guy, innocent guy. So then take him for coffee and then explain all this. Then only you remember. Otherwise you don't remember. So how do you think I remember? Because I am telling you all the time. Okay, like that if you tell someone, you remember. Otherwise you just postpone that. Okay, the first quiz is on next month, June, July sometime, or August or September. Okay, so then we will postpone till that means all the files are deleted, you don't know what is happening at that time. So that is why. Okay, good. So this is what is about the second question, what does a chemical engineer do? You can choose this simplest one, okay, or you can choose this one, which is the very, very complicated step. So it is both extremes, right? But this is really thrilling, as I tell you, really thrilling. Nowadays you have GE, or this is closed already. GM is closed.
Yes, sir.
General Motors are closed.
General Motors closed.
One section, chemical engineering section. Which section is closed? Research section. My God, if you remove that, I think there is no thrill there. Yeah, development is there. Okay, development also, these steps also are very important steps. Lot of thinking is required. In fact, these two steps only in that paper you will read that Carl Bosch steps. How much work he has really done. So that is why this is, I think, at this point of time, at least some people would have definitely explained to you all this when you are in BTech. Okay? I do not know, maybe some teachers would have exposed you to this information, but at that point of time probably you would have not enjoyed like this, but now you will enjoy more. If you come to PhD again after MTech, again if I tell you the same thing, you will enjoy much more. It is not simply repetition, do not feel that it is simply repetition, but I think it is only the memory where you are going to have more and more if it is exposed, if we explain this many times, and this is what is required. If someone asks you now what do you do as a chemical engineer, you can give him a big lecture now, really runs away from you, because you are getting so much information. But earlier I do not know how much, what is the definition of chemical engineering. Definitions we do not have to tell, we do not have to mug up and reproduce, but if you are able to tell what is the meaning of this chemical engineering, what do you do as a chemical engineer, and how are you helping the society as a chemical engineer, that is enough. I hope now you have more confidence on that. What is the next question? How does a chemical process start? This is again very interesting question. How does a chemical process start? Okay, I mean, what is the starting point? Or I think you can also say how does a chemical flow chart start? What is the starting point for any chemical process? Huh? Raw materials. I think this is what is the answer all of us give, which is wrong. It is not raw materials. What do you do with raw materials? I say I give you 2 raw materials, what do you produce? Huh? Please tell, do not be afraid. I say tell. What did you say?
Knowledge. I will process the knowledge.
Knowledge is required, but for a particular process you want to produce, design a particular process, what is the starting point? This is what last 15-20 years also no one is answering immediately. I think 3-4 years back one person told that, sir, the correct answer I will tell you, it is very simple. So then how do you know? You only told me, sir, you came to Tirupati and gave this lecture. You joined here after he was in 3rd year or 2nd year. I think he was remembering and then he told that. No, it is the product which is the starting point. Really, it is the product. I think that we do not know. Maybe it is obvious. You may think that it is quite obvious. I think I tell you with my old experience, now I am 65 years old, not 65, 64 only, 65 means I can't be here, they will throw me out. Yeah. So, my experience is that obvious is not obvious, common sense is not common. These two I really learnt. So, that is why even 1 + 1 = 2 I repeat many times. It is not obvious, and many teachers think that it is obvious and then they ignore that step. That step may be the crucial step for a particular student, beyond that he cannot imagine, but you give that connection, automatically comes. That is why all my teaching is based on really very basic person, starting person. In any course I start only like that, because that is important. Otherwise, okay, at high level I start and then most of them they are not able to connect there, then what is the use? Whom I am talking to? I am talking to benches and then walls, because students are there, a dead space. Okay, because they are there, live and dead, because that is the reason why I tell very simple things also. So that is why it is the product which is the starting point. So what do you do? I think I give you an example. Now let us imagine that now we have on this planet one of the biggest diseases is AIDS, for example, AIDS, cancer. We do not have still good medicine for that, right? Suddenly you think that you have to produce some medicine. Okay, you can recruit a number of chemists and then start doing research, try to find out which medicine may be the best for cancer. Okay. Now what is the starting point? Now cancer drug is the starting point. That is what I told you, that is the starting point for any process. So now suppose you are now successful in identifying a particular drug. You are successful, I think your chemists did, or chemical engineers, you join with them and then try to do together and then finally identify this is the drug which will be useful for cancer. How do you produce this drug? How do you produce that drug? That means how the chemist would have come to that level, that understanding of, okay, this is the product, they would have conducted some reactions. That reaction will have a stoichiometric equation, because you are only putting reactant A, reactant B, giving you the product. That definitely all these steps are required for us. So that means once you identify a drug, and if you are able to produce that drug in a very, very small scale, that means you have a stoichiometric equation ready with you. Okay. So then what is the next point after producing the drug? Now you take the statistics. How many people have cancer? And what is the amount of drug you have to give per patient? Let us say, I think over 1 year, 1 kg he has to take a drug, total amount, because maybe 1 year he has to be treated with this drug. So now you know that how many patients and per patient how much quantity required. Very simple, no? Process calculations. That is why we teach that subject as the first subject. So now you will calculate all this. Okay, so much you have to produce. That automatically determines your plant. You know, Leonspiegel's FA naught in the design expression of reactor. That FA naught is this, right? This drug, how much, I think it is simple, no, to understand. Yeah, we know per patient how much we have to give, how many patients are there. So that will say that okay, now you have to produce 100 tons per day. To produce 100 tons per day, now I have the stoichiometric equation, because we already identified the drug. So that means there must be one stoichiometric equation or more than one stoichiometric equation, more than one step required. So then from that you will back calculate and then find out that okay, if it is 90% conversion, already in the lab when you are identifying drug, when you are conducting that small reaction with small quantities, you know that what is the conversion possible. If 100% conversion is excellent, right. So based on that conversion, now you calculate what will be the reactants you have to produce. Reactants will come there, not in the beginning, right. I think you told no reactants. Yeah. So that reactants will come only after that, and that much reactants you have to produce. I mean, you have to send to the reactor where you have that FA naught. I think when you write that equation, I will again remind you there. That FA naught starts. Okay, good. Now you have only one. I think in that reactor design expression, because you already done 2 reaction engineering courses, most of you, there are 4 parameters. One is FA naught, other one is minus RA. Yeah. Other one is XA. XA only. Yeah. Other one is volume. I hate tau, because tau is not required at all. In the design expression you will never get tau, you will get only V by FA naught. Okay. If you want to convert that V into tau by dividing something else, you do it, but not required directly. So volume, first one is volume, conversion, reaction rate and FA naught. These are the 4. Out of these 4 you know FA naught. How do you get FA naught? The reactant, how much you have to send to the reactor, you get only from market survey. There you can employ MBAs. You can ask them to go to the market and then try to find out how many people are patients and how much they require, all that information. So one parameter you have already decided, but now you in the laboratory you just proved on a very small scale whether reaction is feasible or not, but you don't know exactly what are the temperatures, because I told you some temperature you use and then shake it and then try to produce, and one small wait for some time and then take that product out, analyze. If you get the product, you jump up and down that you got the product. You never really bothered about what is the exact temperature I have to use, or what is the range of temperature we have to use, because in any reactor you cannot exactly maintain only 100 degrees centigrade. Either it goes to 105 or it may go to 95, some range you require. How do you get this information? You have the stoichiometric equation, and from stoichiometric equation you can get lots of information. I think most of you may not think about this. No? What is the information you can get from stoichiometry, Gani?
The raw materials required.
That's all, you already used that, you have not calculated. Apart from that, what do you get? See, these are again obvious things if I tell you, but I think we don't think that. The first thing that can tell you is that whether the reaction is heterogeneous or homogeneous. How do you know? Because reactant A, reactant B, what is the physical status? Okay. So that can give you whether the reaction is heterogeneous or homogeneous. So stoichiometry can give you hetero or homogeneous reaction. So what else it can give? Excellent. Exothermic or endothermic? exothermic or endothermic. So still what information it can give?
Condition, temperature.
How does that give you temperature condition, temperature, pressure? Yeah, Merit, you are telling something? Excellent. Reversible or irreversible, it will give you an idea. That means by looking at that you cannot say, but by conducting again some reactions only you can find out whether it is reversible or irreversible. But you can also do that using thermodynamics, because here stoichiometry, when you are using stoichiometric equation, how do you calculate delta F? You need stoichiometric equation, right? So free energy also you can calculate from stoichiometric equation. How do you calculate enthalpy? That will give you, in fact here homogeneous, exothermic or endothermic. Delta H, when you calculate, that will tell you whether it is positive, endothermic, negative, exothermic. So that is the information what you get. And free energy, what information you can get from free energy? Whether the reaction first of all is possible or not. Okay. So then that delta free energy delta G you will equate with minus RT and RT ln K. What is that K? Equilibrium constant. If K is very large, what is your prediction?
Irreversible.
Forward reaction. That gives you whether you have yeah, I think someone was telling, reversible or irreversible. Yeah, reversible or irreversible. Okay. So you see how much information you can get that simple stoichiometric equation, all from thermodynamics, right? And because free energy thermodynamic data you need to calculate, and delta HR again thermodynamic data you need to calculate, and that will give you whether the system is exothermic, endothermic and all that. Okay. And even this equation free energy will give you reversible and irreversible, and not only that, it will also fix temperature and pressure. That is what I think someone was telling there. At this point of time, when you have delta G equal to minus RT ln K, so this K and RT is there. So for every T there is a K, and for temperature, pressure also if you change, then you will know what will be the equilibrium conversions, XAE, right. So that maximum conversion that is possible is dictated by this equation, and that is connected with temperatures. That is what I asked one of the questions in your the first test, conversion versus temperature for exothermic reaction, endothermic reaction. Okay, that we will do later, we will do that. Okay. So all this information you will get from stoichiometric equation. This is stoichiometric equation. Okay. From that you see how much information, but now you see we have used thermodynamics data or thermodynamic subject, we have to understand, and process calculations we have to also understand, and these two subjects automatically come there. So then what is the next step? You have started with a product and it was feasible on very small scale, but you do not know what will be the temperature conditions, whether there is a variation, in that variation what will be the changes in equilibrium conversion, all that you do not know, all that data now you got. What is the next step? What information you get still from this stoichiometric equation? Can you tell me, if I have A plus B going to R, what is the order of reaction? This is stoichiometry. You can't, right? Because so how do you know whether the equation is first order, second order? Yeah, if it is elementary, I know. How do you know it is elementary? By looking at that. How do you know that I am good guy or bad guy when you look at me? Impossible. No, I can be a dangerous fellow, okay, or I can be a very good fellow. We don't know. Okay. So that is why by looking at the reactions like people, we cannot find out whether this is what is the order of reaction. So that is why experiment is a must. You do not have any other choice. You have to do an experiment. Even kinetic theory of gases will beautifully tell me if it is gas phase reaction. This is A gas, B gas giving you R gas. Then our imagination goes, one molecule of A and one molecule of B, they come together, they collide. All energetic collisions will produce R. All that beautiful theory is there. right. It is only beautiful theory because at molecular level we can't imagine. Molecules are so small, I think you cannot imagine that, but still you do the calculations from theory and then find out from the experiment whether your theory is right or wrong. If the theory is not correct, change the theory and again measure and then try to find out. Okay. So, next step is, after finding out all these, next step is kinetics. Kinetics only will give you whether you have order of reaction or whether whether there is no order of reaction, that is also possible. It is not that always I should have order of reaction for this. I may have a very complicated equation where you cannot talk about order. Yeah. Now you see we have come to the kinetics part. So, I am just trying to tell you the sequence of subjects also. First one is process calculations. Second subject normally you taught is thermodynamics. Thermodynamics and fluid mechanics simultaneously they come, and then of course heat transfer and all that will come. All exothermic reaction means now you have to imagine it is highly exothermic. The reactor will get heated up. Now I have to remove heat from the reactor, then heat transfer automatically comes. And now after the reaction is over, it is liquid phase. Let us imagine for easy imagination, and this liquid phase has now reactants and also products, right. Yeah. So, then we have to separate them. The easiest process we can imagine is distillation. So, that fixes even downstream operations. So, once you fix that distillation is possible, and now you use distillation column design, okay. Mass transfer, you have come to mass transfer. Under what condition distillation is not possible? I have the liquid phase. Azeotrope also we have now become experts, no? Yeah, I think in the simplest language, if the boiling points are very close, then your distillation column will reach moon height. Yeah, it has to touch moon. So, moon will feel traffic jam and all that. So, I think so that kind of long tall reactors we do not have to really design. So, that is the reason why you go to the next operation. What is the next operation? Extraction. But extraction again you cannot avoid distillation. Yeah, yeah. No, you again separate into some other component, and again you have to separate those two, right. So, that is how all downstream processing is designed. So, now mass transfer automatically came, right. So, like that in now if you want to start from the heat exchanger, because the temperature 100 degrees centigrade you have to heat them, and the reactants have to flow through heat exchanger, then go to reactor, from reactor to distillation column, from distillation column to maybe storage tank, all everywhere you have the flow involved. That is why we teach fluid mechanics. Now, you see fluid mechanics have come, thermodynamics, process calculations, heat transfer, mass transfer, and reaction engineering will come. Without talking any reactor, we have talked all this. We said only it goes to reactor. So, in actually what reactor you take, okay, and what process you take, whether it is continuous process or batch process, all that will come in chemical reaction engineering. And for all this we need control. 100 degrees means you need 100 degrees centigrade. How do you control? Or even concentration of in a distillation column, okay. Those concentrations can be again controlled by temperature control inside the distillation column, right. So, that is why control automatically comes, and the chemical technology will give you the real information about what is chemical engineering. All subjects covered. Yeah, and afterwards of course, you have plant design and equipment design, all that only to supplement this. That is why the entire chemical engineering is only based on 5 or 6 subjects. Any plant you bring, that is the greatest of chemical engineering. Any product you think, only these 5 subjects are enough. Okay, if you put everything in transport phenomena, mass, heat and momentum, then CRE, thermodynamics, process calculations, that is all, these are the subjects, and of course control should help you. Okay. So, how does a chemical process start? Means with a product, and now with all this information you have a flow chart with you. I do not know whether you noticed it, that almost I told you how to develop a flow chart. How do you develop a flow chart? We have first told that you identify the product, and then you try to find out through the stoichiometric equation what is the total amount of material, right. Yeah. Now, from thermodynamics you will find out the temperature and pressure. So, that means now we have the reactants are available for you, that is A plus B is available. Now, temperature is 200 degrees centigrade. So, that means and these A and B are available only at room temperature. Now, you have to heat them to 200 degrees centigrade and send it to reactor, or you can also heat that inside the reactor itself, that becomes a batch system. But when you have the continuous system, so you have to send the reactants continuously through the heat exchanger. That is one of the equipment in the flow chart. The first is storage tank, pumps, then heat exchanger 200 degrees centigrade, right. So, that means it is entering at 30 degrees or 40 degrees centigrade and leaving at 200 degrees centigrade. Now, you have heat exchanger in between, then that goes to reactor, and reactor you have the liquid product for as an example. Then you will have, if it is a gas product, again you can imagine what is the downstream operation. Then in the reactor you have the liquid, boiling points are very far, then you know distillation is the operation what you have to use, then distillation column. Now, you draw the flow chart, it is very simple for you. That is how I feel we have to teach chemical technology. You explain the process clearly, and then automatically the equipment will fall there. We do not teach that, we first draw that, and this is the heat exchanger, this is the reactor, this is distillation column, this is finally storage tank, that is what we explain, without telling the real process. And most of the teachers, we do not know how to teach chemical technology nicely. That is what I told you, the Russians have only teach like that, their books are all focused on that every step. So, if you understand every step there, and the conditions are given from thermodynamics. In fact, they in chemical technology book, they also calculate from thermodynamics what is free energy, what are the temperatures possible, what are the pressures, what are the conversions, everything they calculate. That gives the overall picture. But problem is, why we do not teach in that way is, entire semester you can teach only one flow chart, and there are how many flow charts? You have rubber, you have cement, I am just telling inorganic things, still how many things are there? Paper, plastics, soaps, alkalis, so many, you see, so many things are coming. So, that is the reason why everything mug up quickly and then say that these are the things, but that gives you the real feeling for chemical engineering. Chemical technology gives you the real feeling for chemical engineering. So, this is what I wanted to tell you in the third question. How does a chemical process start? Means it is almost development of a flow chart. Equipment automatically falls into that. This is the overall picture what you get now from that question. Okay? I think we will stop here.